To all of the sponsors and to the Platinum sponsors. I think this then kicks off Zero Knowledge Summit 7, and I'd like to invite the first speaker to the stage, Pratyush from Aleo, who's going to be talking about efficient private delegation of zkSNARK provers. Welcome, Pratyush.
Okay. All right. Hi, everyone. Fantastic to be here and see a lot of familiar faces and not familiar faces also in person. OK, my slides are up, and this clicker might run out of battery, but let's see. OK, fantastic. You can see what I'm talking about. OK, so yeah, hi, everyone. I'm Pratyush, and today I'll be presenting our work on delegating or outsourcing zkSNARK provers in a privacy-preserving manner. This is joint work with my excellent co-authors, Alessandro, Ryan, and Yuno. OK, let's get started. So we all, no one loves zkSNARKs here, but I'll still quickly recap what they do. So zkSNARK is a protocol for a prover to convince a verifier that some statement is true without revealing why it's true, so hiding some secrets, and in a way that the verifier can check quickly, right? The succinct proof is very efficiently checkable. You can see the stuff at the bottom, right? OK, fantastic. So there's many applications of zkSNARKs, in particular the zk part, leaving aside the succinctness. You have things like private transactions, private smart contracts, some of which people talked about just a minute ago. Things like decentralized hidden information multiplayer games, and many more, right? So there's a lot of cool things you can do with these zkSNARKs. But unfortunately, applying these SNARKs to these applications, you run into one bottleneck. And that's proving, right? We all know that proving is really, really, really slow. So if you're trying to prove, like, say hash is 10 kilobytes of data with SHA-2, then it's going to take like over 2 minutes, but it just takes a couple of milliseconds, or maybe not even that, I don't know, microseconds on your computer, right? So SNARKs are slow. So one thing you can try to do is just say, OK, I'm not going to run it on my phone. I'm just going to throw it off to the cloud and have some powerful machine run it for me and give me back the result after running the prover in some amount of time. And if your computation is particularly large, you can even do things like use a cluster, like a Spark cluster, to run your computation. And this is work. There's a paper called DISIC, which shows how to do this, right? And you get very nice scalability. OK, but the problem with all of these techniques, is that you reveal your secret information to the worker that you're using, right? That cluster or the individual server learns your secret witness, which you wanted to keep hidden. OK, so ideally, we want to outsource proving, but with privacy. We want to hide the witness while still not doing the work of generating the proof, right? So what we want is a delegation protocol or a scheme where the delegator can obfuscate the witness before sending it off to the cloud in some way. And then there's maybe some interaction between the cloud and the delegator. And in the end, the delegator gets back this proof that they can give to whoever they want. All right? So what we want from these delegation protocols is, first, it should be efficient, right? It should be much cheaper to outsource your proving to the cloud than it is to do it locally, because otherwise there's no point, right? Second, the delegator's witness should be hidden from the worker. So this is the privacy goal, right? We don't want to reveal the witness. Again, otherwise we would just do it on our machine. OK, now the problem is that straightforward approaches to this using MPC and like FHE are really heavyweight. So when you try to use like cryptographic tools, your total runtime is going to far exceed the running time of like doing it on your device. So you don't want to do that. So if you want to just use a single server, you can't do that. So maybe what you can do is you can sort of relax the security guarantee a little bit and say, we only care about threshold privacy. So I'll outsource my proving to a set of machines. And they can interact and compute the proof for me via some sort of cryptographic protocol. And the guarantee that I want is that now, as long as one of these workers is honest and doesn't collude with the others, my witness is hidden, right? So as long as one machine is behaving honestly, you're fine. So you think maybe one of those machines is AWS, one is Google Cloud, and the other one is Azure or something like that, right? So they might not be colluding with each other for competitive reasons. Okay, so this is sort of a more achievable looking goal. So let's see what we could do. Okay, so what we do in this work, which is not yet online, is construct exactly these kinds of delegation protocols for zkSNARK provers for these popular class of zkSNARKs, which rely on polynomial IOP. So things like Plonk, Marlin, Sonic, every sort of recent work on zkSNARKs falls into this category. And we show how to construct delegation schemes for this entire class of SNARKs by constructing first delegation schemes for polynomial commitments, which I'll talk about in a couple of minutes. And then for the polynomial IOP itself, and then finally a compiler which takes these two delegation schemes for the subcomponents and constructs a delegation scheme for the entire zkSNARK. All right. So it's not just a theory paper, because otherwise, I had a very concrete motivation. It'd be kind of disappointing to say, okay, I'm done with the proof. So we actually implemented and evaluated our protocols, and we have a bunch of metrics that I'll talk about at the end of the paper. But the TLDR is that when you're delegating from your phone to this cloud server, generating the proof end-to-end takes 26x less time, right? So that 140 seconds becomes like 5 seconds. So this may be more reasonable, if I have my math correct. Okay. All right, so the strawman, so let's see how we can do this. The strawman technique is to use what's called MPC, or multi-party computation. This is a cryptographic technique which allows a bunch of parties which don't want to collude with each other, which have some interest in keeping data disjoint from each other, to jointly compute on their data in a way that they get the result, but no party learns any information about the other party's inputs, right? So every party's input is kept secret. So basically, it's a way to do distributed computing on secret data. All right, so you could just throw this generic crypto tool at it. But the problem is that off-the-shelf MPC tools are very, 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 very expensive. They also require expressing your prover algorithm as this arithmetic circuit, which you might be familiar with in the context of zkSNARKs. Very similar thing happens for these MPC protocols. Yeah, but the problem ends up being that the prover circuit itself ends up being, again, very, very large for any of these zkSNARKs that I talked about. All right, so why is this circuit large? So as I said, we'll focus on this class of SNARKs which rely on polynomial IOPs and polynomial commitments. So polynomial IOP, for those who are not familiar, is an interactive protocol between a prover and a verifier, where the prover's messages are polynomials, okay? So sort of, this includes Sonic, Marlin, basically all the protocols I talked about on the slide there. And the other component is what's called a polynomial commitment scheme. So this is a thing, a primitive, Anna, I guess, had the very useful descriptions. But basically, it allows you to commit to a polynomial and then later prove that the evaluation of that polynomial at some point is correct, is the claimed evaluation, okay? And again, we have many instantiations of these, such as the KZG10 one, things based on inner product arguments, dark, Hyrax, a bunch of things, okay? Even Fry, right? So the zkSNARK prover circuit consists of subcircuits for both of these components, and both of these are like fairly heavy cryptographic objects, right? As I said, can themselves be quite complex, right? So we want to simplify both that plus sign and the two little boxes inside as well. So let's see how we can do it. Let's see how we can, start solving part one. So before I dive in, I'll do like a very quick, very whirlwind recap of how you can construct these, because it will be useful in the construction later. I think I'm doing okay on time, but yeah, let's see. All right. So in these SNARKs, which rely on these polynomial IOPs, what you do is the zkSNARK prover runs the polynomial IOP prover, and the same thing for the verifier, it runs the polynomial IOP verifier. The prover, it produces some polynomial, you commit to it using a polynomial commitment, send over the commitment. The verifier runs the PIOP verifier, you send back the challenge, whatever. You repeat this for a bunch of rounds, you get some commitments, okay? And then comes the query phase, where you have to prove that these committed polynomials, when you evaluate them at some query set, the evaluations are correct. Okay? This is a whirlwind overview. You don't need to understand too much, but just basically the takeaway is that you produce the polynomials and you commit to them. Okay? And then you later prove that those committed polynomials evaluate to whatever you claim they evaluate. Okay? All right. Maybe I should stop for questions at this point. Any questions about anything? No? Okay, I'll go on. Feel free to stop me within, I guess, time bounds. All right, okay, so this is basically the structure of these zkSNARKs. The other building block that we'll be using before we dive in is this notion of additive secret shares. You might have heard of Shamir's secret sharing. This is a very simple version of that, which basically says that you can take your message and split it up into like n chunks or shares, such that as long as you don't have all n of them, you don't leak any privacy. Even if you have at most n-1 of the secret shares for a given message, you can't learn any information at all about that message. Okay? On the other hand, if you have all n shares, you can combine all of them and get your message back. And the other interesting property that we'll care about is this thing called homomorphism or additive homomorphism, which says that if I have a secret share of A and a secret share of B, I can just add those secret shares and get a secret share for A plus B. Okay? So this is called additive homomorphism in cryptography. It'll be useful in just a second. All right. I think I'm speaking fast, so I'll try to slow down a bit. All right, so let's handle each of our problems one by one, starting with this issue of combining subcircuits, right? So the problem that we had was we're just trying to take the zkSNARK prover as a monolithic object and throwing an MPC protocol at it, right? But actually, our zkSNARK prover has this underlying structure, so let's try to exploit that. So we'll take advantage of this modular nature of the prover and say, instead of doing a monolithic MPC, we'll construct an MPC for delegating just the polynomial IOP, and we'll combine it with an MPC protocol just for delegating the polynomial commitment scheme, and this will give us our protocol for delegating the zkSNARK. All right, so this is the high-level structure. I'll talk a little bit about what this combining step looks like, and then we'll dive into how to actually construct each of those boxes on your left, my left, or whatever. Okay. All right, so let's see how we can do this. So let's say we have these two boxes as given, right? How we start off with is the delegator sends secret shares of the witness to each of the, let's say there's only two machines in this example, right? To each of the two worker machines. Then what they do is they take these secret shares and they invoke this MPC for the PIOP prover and get secret shares of the first polynomial, so the polynomial produced in the first round, for example, okay? Then what they do is that they'll invoke the MPC for delegating PC schemes and get the commitment for that polynomial, shares of the commitment for that first round polynomial, okay? And then they can do the same thing as you saw in the sort of the standard Snark. They just repeat these two operations over and over again in sequence until they have this vector of polynomials and vector of commitments corresponding to all of the rounds. And then they can run the sort of proving step to produce the evaluation proof for these commitments, right? Okay, so the structure is basically the same as that slide earlier. We just replace sort of running the IOP prover and the PC scheme committer locally. You just replace that with these MPC protocols for doing the same. Okay, so the high-level structure is very clear. Okay, so at the end of doing this, now these workers, they have shares of the final zkSNARK proof, right? They have shares of the commitments, they have shares of the evaluation proof, and they have shares of the evaluations themselves. So they send this stuff back to the delegator, who can combine these shares and recover the actual zkSNARK proof, which it can go use in whatever application it wanted to use. Okay, so that solves problem one. Any questions on that? Yeah.
Wait. Actually,
Afterwards?
I wonder. Yeah. So you're going to do talk, question, talk, question?
I can do either way.
We have to get it on the mic for it to work. So, sure.
Okay. Sorry. I should have asked before.
So my question is how you compute challenges.
So that's a very good question. So what you can just do is you can select. Actually, that previous diagram, I lied a little bit. You can actually, it's okay for the commitments to be sent all to one party. So this fellow on the bottom can send his share of commitments to the worker on the top, right? And it can combine it, and then you can get the actual commitments in the clear and run the random oracle on those. You could also send it back to the delegator, and the delegator could give you the random oracle challenge. That's another idea that you could use. We have a couple of different variations in the paper, which is not online yet. Yeah, very good question.
I think there's another one here.
So for something like Plonk, you'd have to compute something not added, like you'd have to multiply two polynomials together, for example, to get a polynomial later round. So the diagram showed only interaction between the servers, but I'm imagining that there would be continual interaction between the phone as well, right?
That depends, again, on the setting. I'll get into it when I talk about how you actually implement both of the boxes. Yeah. OK, very good questions. All right. So that's, I guess, a high-level overview of the compiler, which takes these two delegation schemes for the underlying components. So let's see how we can actually construct these underlying delegation schemes. All right. So, and that's solving the problem of getting cheap subcomponents. OK. So we'll start off with constructing delegation schemes for our PIOP provers, right? So that's what we want. We want something which says, given a secret share of the state of the prover at a given point, at a given round, give me the polynomial for that round, right? Or secret shares of the polynomial for that round. Okay. Now the operations, before we can talk about how to speed this up, right, or how to implement it efficiently, we have to figure out what operations are actually done by these PIOP provers. And by and large, for all of the SNARKs that we care about, I think, these operations are just basically these four. You want to evaluate your polynomial over some multiplicative subgroup, your evaluation domain, if that's a better term for you. You want to divide your polynomial by some vanishing polynomial of that same subgroup. You want to do some affine operations, additions, subtractions, adding a constant or something. And finally, you might want to do some polynomial multiplications, right, between secret shared polynomials. So the good thing is that the first three of these, they can all be implemented via linear operations on your secret shared polynomial. So this doesn't require any interaction between the workers at all, right? So this is very efficient to do. You just do local operations on your polynomials, and you can get the secret shares of those results. But for polynomial multiplications, that's not quite true. To multiply two polynomials of, say, degree d, what you have to do is, this is getting a bit technical, but bear with me. Use an FFT to get the evaluations of your polynomials over your subgroup or your multiplication or your evaluation domain. You do a pointwise multiplication between these evaluations, and then you do an inverse FFT to get to interpolation to go from these evaluations back to coefficient form, right? So it's a whirlwind overview of polynomial multiplication. Now the nice thing is that steps 1 and 3 are again linear. They're just FFTs, so they don't require anything, any sort of secret multiplications. But unfortunately for us, step 2 is a multiplication between two secret shares, right? And our secret shares, they have additive homomorphism, but they don't have multiplicative homomorphism. So you can't just multiply two secret shares and expect to get a secret share of the product. But thankfully, in our setting, and again, normally this is the key sticking point in a lot of MPC, this handling multiplications or AND gates is the very expensive part of MPC protocols. But in our setting, we have a helper. We have the delegator. So what we can do is, if your workers have secret shares of two things they want to multiply, they can just send those secret shares back to the delegator, who can just combine the secret shares, compute the product, and send back fresh shares of the product, right? So we're really we can leverage this delegator. And the key thing here is that field multiplications are very cheap, right? So I'm not asking the delegator to do something like a multi-scalar multiplication, which is expensive and kind of would defeat the purpose of delegation, right? But these field multiplications, you can do them in like a few nanoseconds, right? They're quite efficient. All right, so this is how we can leverage the delegator to get very cheap polynomial multiplications with just one round of interaction with the delegator. And actually, in the paper, we have other techniques that you can use. The delegator doesn't even have to be around during the execution of the protocol. You can just send some pre-processed material beforehand and then sort of go offline and just receive the proof at the end. But that's for the paper. OK, so this is how we can very efficiently implement like 99% of the operations that happen in modern zkSNARK or PIOP provers. All right, so that handles the first component. What about delegating PC schemes? So I'll particularly look at the KZG10, because, polynomial commitment scheme, because that's the most popular one. And recall that we want to do two things. We want to first take a secret share of a polynomial and get a secret share of the commitment. And then, given the secret share of the polynomial and an evaluation point, I want to prove that the committed polynomial actually evaluates to whatever the claimed evaluation is, right? So the two things I want to do, committing and opening. In terms of committing, the cool thing is that the commitment scheme is linearly homomorphic also. So a commitment to the shares of the polynomial is a share of the commitment to the polynomial. Yes, I got that right. OK. So just assume that your vector of the shares has this structure. Then a share of the commitment is just the standard thing that you would do with KZG, which is compute the multiscalar multiplication, right? So there's really almost no difference from the actual KZG algorithm. And the same thing when you actually want to produce the evaluation proof. You compute your share of the witness polynomial, which is this quotient thingy, right? Yeah, whatever that expression is. And the cool thing is that this also does not require any secret multiplications. This is a linear operation. So basically, the takeaway is that the complexity is literally the same as the standard KZG on non-shared or non-secret shared polynomials. So committing to a secret shared polynomial and proving its evaluation is literally the same. There's no difference here. So that's, I guess, wraps up the two components. OK, yeah, I just want to say there's a couple of other recent papers that have appeared which have similar techniques to the stuff that I've mentioned just now in different contexts, not for delegation, but for like MPC over proving over shared data. OK, so there's tons more optimizations in the papers. You can really take an advantage, large advantage of the the setting of you have a trusted third party in some sense to do the expensive operations, a few of the expensive operations for you. OK, this is working again. All right, so we have the optimizations on the crypto techniques as well as on the system side. When the paper is online, I would encourage you to read it. So we've solved, at least hopefully, both problems 1 and 2. So the question is, OK, I've talked a lot about theory and things of polynomials and all this garbage, OK? But the question is, does this actually result in concrete performance improvements? Can you actually take these protocols and get something and implement it and get an actual speed up for your application today? And the answer is, thankfully, yes. We implemented this using ArcWorks. It's me, so I would do ArcWorks, obviously. But yeah, so we have delegation protocols for KZG. We want to implement it for the inner product argument scheme as well. For the Marlin PIOP, but it should be fairly straightforward to extend it to things like Plonk, whichever variant of Plonk you want. And by putting it together with our compiler, we get a delegation scheme for the Marlin Snark. Okay. In terms of actual concrete performance, we evaluated these schemes in like sort of 3 different settings: a laptop which has very fast internet access, and here you can see there's a latency reduction of 9x compared to normal execution. But something that's really interesting is that, I guess the last 2 columns, the first one says how much time does the delegator actually spend actively computing something versus waiting for stuff to be computed, right? And the answer is that active computation goes down by 600 times almost. So this is like a massive energy savings, you can do whatever else you want on your computer in the meanwhile. Another benefit is that you can actually prove much larger instances within the same memory budget compared to if you were proving it locally, right? So this is 256 times larger. So if you could prove something of a size 1 million on your computer, now you can outsource the computation and prove a circuit of 256 million constraints, which is kind of insane, right? Okay. The other settings are a laptop with the standard home internet, and here we see sort of less impressive numbers because the communication overhead back and forth between the delegator becomes kind of problematic. And the final one is doing the same experiments on a mobile phone. And here, because the phone is so much weaker, even despite the slower internet, you're still able to see quite large performance improvements. All right, so that sort of wraps up my presentation, I think. Yeah, so the paper is coming soon to an e-print near you, and the code also, hopefully. Yeah, fantastic. Thank you, everyone.
Two questions up front.
Hello. So I have a question or maybe a suggestion how to possibly make your this fantastic thing is like 30 times better. So actually in many prover use cases, well, the number of possible witnesses is small. For example, recall like Zcash or Tornado Cache, you have a tree like to the 32 layers, to the 32 possible leaves, and to every leaf you prove that you know a preimage. But actually, you can delegate all possible paths from a leaf to the root to delegators. They compute like 2 to 32 leaves, and you retrieve one of them using private information retrieval, for example. And you yourself, you compute only a proof for like this tiny thing, which is 30 times smaller. And this one you can delegate using this thing. So you can, but if you are able to combine their proof for like almost the full path with your proof for hash preimage, then you can make it like 30 times faster.
Yeah, so no, that's a cool technique. Does that require sort of splitting up the circuit into something that I guess you pre-process and then later on? Yeah, I think so that I guess the motivation of this work was to just say, I don't want the application developers to do anything for their applications. You just want to, literally like you can use any existing verifier to do this. But yeah, I think that's a cool technique. And yeah, there's a lot of application level optimizations that you can also do combined with this and other techniques like your idea.
Hi, maybe a trivial question. How easy is it to find faulty or malicious workers?
How easy is it to find a faulty, sorry, what?
Faulty workers, like.
Yeah, so in some sense, the result of the computation is self-verifying, right? Like if the worker is cheating, then you'll get an incorrect proof, right? Otherwise, you sort of broken the soundness property of your zkSNARK, right? So from that perspective, it's like at the end you'll know when you have something that's correct or not. From a liveness perspective, it's not like this protocol, at least in like the instantiation that we have in the paper. It's not the greatest because one of the workers could just decide to like drop out, and then you're waiting for that worker to finish. So you might have a timeout or something. So they can do like a denial of service attack. But otherwise, in terms of actually influencing the correctness of the proof, there's not anything they can do. That's not detectable.
Any other questions?
I was wondering, does it, this ability to produce shares of the polynomials, does it also presuppose that the circuit itself has been somehow cut up into shares of the circuit, as it were? And what is the communication between the different workers, basically?
So that's linear in the circuit size. It's not like something like DZIC or like sort of each worker is not doing a chunk of the computation. They're doing basically like the full prover computation with some caveats, which it'd be very interesting to see how you could combine techniques from DZIC with this work to see how you can reduce the load at each worker. That'd be very interesting future work, I think. Yeah, great questions. I think there's a question all the way back.
So KZG polynomial commitment seems to be quite MPC friendly, right? Mm-hmm. What if you use something that utilizes stuff from Fry, like Fry-based polynomial commitment?
Yeah, there's a couple of things. That's a good question. There's a couple of things you can do there. So the problem with Fry is that it's all hashes, right? So there's no additive homomorphism that you can leverage. What you can do is at the very leaves, you can say, I'm going to commit my Merkle tree is going to be built over additively homomorphic commitments, for example. And then the workers exchange those commitments, and at the end, somebody builds a Merkle tree over the commitments. So you'll have commitments to the secret shares, which are secret shares of the commitments, right? Unfortunately, from a delegation perspective, that doesn't make too much sense because the cost of computing those commitments is very high, much higher than the Merkle tree cost itself. So you might end up with like an overall slower prover, but it might be helpful in other protocols, like where you just care about privacy and not actually delegating. There's also other things. I think the OB22 paper, they have another protocol where the proof size grows logarithmically with the number of workers. Basically, build like a mini Merkle tree at the leaf consisting of all the workers' shares. You can do that also. Yeah.
If you use MPC-friendly hash, right?
Sorry, who just asked that question? Can you say it into a mic?
I can repeat the question also.
Or that.
Yeah. So the question was just, can you, for this fry technique, can you actually use MPC-friendly hashes? So I think it doesn't work. You would pay a large cost just because you'd be running your hashes inside MPC, which is expensive. We wanted to avoid running any expensive crypto in like off-the-shelf MPC. Yeah. No worries.
Okay, there's another one over here.
Okay.
So depending on how many workers you pick, the global energy usage may be higher than.
It will go up, yes.
So what do you think is a reasonable trade-off in terms of total energy usage and?
I think it depends on like sort of the cost of privacy in your application and the cost of privacy to the user in particular. Like if I don't care about particular Zcash transaction, somebody knowing where it's going, then I can just do it on my computer. But if I'm like a very paranoid person, then I might. But I don't have a good computer because I don't trust powerful computers. So then in that case, I might outsource and be willing to eat the additional energy cost. There are things that you can do to optimize it so that the work at, like all the workers are not doing like all of the protocol, all of the prover work. In particular, if your protocol has this sort of structure where parts of it are witness independent, then only one worker has to do it. So for those things, it's not any more inefficient compared to running it on your own device. So for example, Marlin has that structure.
Any further questions? All right, one at the front, or almost front.
Some practical one. When you compared the phone implementation, that was also ArcWorks?
Yeah.
Okay.
Yeah. I mean, imagine you could have like a more optimized implementation, but I think sort of any optimizations that target your phone would also hopefully translate to your server implementation.
Thank you.
Anyone else? If not, then thank you so much, Pratyush, for the talk.
Thank you so much, everyone.